In this video, we are going to learn how to test polar equations for symmetry. Now, symmetry for a graph would be a reflection across a particular axis or a line or even a point, and you'll get the same graph. So first, we're going to look at symmetry with respect to the polar axis, which we sometimes know as the positive x-axis, meaning any point that is above that axis could also be reflected below it, and both of those points would remain in the same equation. The way you would test this is if you have a certain point r theta, the point reflected across the polar axis would be the same point r, comma, but negative theta since I rotate the other direction. So if I just replace theta with negative theta, I should get the same equation. If it's not the same, then there's no guarantee that it's symmetric with respect to the polar axis. So you'll see here we have r sine theta tangent theta. If I plug in negative theta, I can if I put the equal sign there, if I plug that in, I can get r is equal to, sine is an odd function, so that's negative sine theta. I can rewrite it as, and tangent of negative theta is also an odd function, so I can rewrite that as negative tangent of theta. And then negative sine theta times negative tangent of theta is equal to r, is equivalent to r is equal to sine of theta tangent of theta, which is the same equation. So this function would be symmetric with respect to the polar axis. Now next we can test for symmetry with respect to the line pi over 2, that vertical line, which means that any point you're given r theta, you can also find an equivalent point on the graph at r pi minus theta, with pi being a half rotation, and then you take away this rotation, which is equivalent to theta, which is where we get pi minus theta. So if I replace theta with pi minus theta, and if I end up with this equivalent equation, then it should be symmetric about that line. So if I have r is equal to 3 plus sine of theta, if I replace theta with pi minus theta, I should be able to rewrite this equation to look the same as this one if it is symmetric with respect to the line. So how do we check that? Well, we just use the difference formula for sine, which means that this could be rewritten as 3 plus sine of pi cosine of theta minus cosine of pi sine of theta, which gives me 3 plus sine of pi is 0, minus cosine of pi is negative 1, sine of theta, which gives me r is equal to 3. This is 0, and minus negative 1, so plus sine of theta, which is the same. So I know that's symmetric about that line. Now lastly, we can check for symmetry with respect to the pole or origin, meaning any point that's at r theta can be rotated at 180 degrees to land at another point directly across from it through the pole. So that's why we say symmetric to the pole, which is that origin. The way you find this is either you look at the negative radius from r theta, which means replacing r with negative r, or you replace theta with theta plus another half rotation, pi. So we're going to check it for negative r, and if that happens to not work, we would also check with theta plus pi to see if that one could work. But to check, if I had negative r, if I had r squared equals 9 cosine of 2 theta, if I replace r with negative r squared is just the same as r squared, which gives me the same equation. So I don't need to check the other one. This is symmetric to the pole, which often means that it is symmetric with respect to the line. Pi theta is equal to pi over 2 and the polar axis. You get both if this one's true. Now let's test this out with a few examples. Now one thing to keep in mind is that even if it fails a test, it could still be symmetric about that axis. What we call that is sufficient but not necessary. So these 3 tests are sufficient but not necessary for symmetry. Which just means that if it does pass, then it definitely is symmetric. If it doesn't pass, doesn't mean it's not symmetric. You may just have to graph to find out. But we're going to check for symmetry using these tests. So first we have r is equal to 2 plus 4 cosine of theta. So we're going to try out this first test by replacing theta with negative theta. So r is equal to 2 plus 4 cosine of negative theta. Cosine's an even function, so I can eliminate that negative inside of it. And it gives me r is equal to 2 plus 4 cosine of theta, which is the exact same function. So we say symmetric with respect to WRT, the polar axis. Now let's test out the other ones to see if it has multiple symmetries. Now, in a polar equation, if you replace theta with pi minus theta and you get the same equation, then it would be symmetric with respect to the line pi over theta equals pi over 2. So I'll replace theta with pi minus theta, and I'll use the difference formula for cosine. So it gives me 2 plus 4 times cosine of pi times cosine of theta plus sine of pi sine of theta, which gives me 2 plus 4 times cosine of pi is negative 1. Sine of pi is 0. So simplifying all of this, I'm left with 2. And when I distribute the 4, minus 4 cosine of theta, and then plus 0. But this is not equivalent, so it would not be symmetric with respect to that line. Which usually means if it's not symmetric to both of these, that it wouldn't be symmetric to the pole, but we can still test to see. So you can see that change. First, we can try the negative r test. And if I divide by negative 1, I'll get r is equal to negative 2 minus 4 cosine of theta, which is not the same equation, so that one fails as well. But I could also try the theta plus pi. So r is equal to 2 plus 4 cosine of theta plus pi, which I will use the sum formula for cosine. So 2 plus 4 times cosine of theta, cosine of pi, but minus sine of theta, sine of pi. This gives me 2 plus 4 times cosine of theta times negative 1 minus sine of theta. Oop, that should have been a pi. I wrote theta twice. Sine of theta, which is 0. So that would go to 0. This is negative cosine, leaving me with r is equal to 2 minus 4 cosine of theta, which means that it is not equivalent, so its only symmetry is with the polar axis. So all of these tests, and I say 3 tests even though I did 4, because there's 2 ways you can do the pole. And you want to check both, because one might work and the other one might not. But let's try it with r is equal to 2 sine of theta. So if I try the first test to see if it's symmetric with the polar axis, I get r is equal to 2 sine of negative theta, which, since this is an odd function, the negative can come out, give me r is equal to negative 2 sine of theta, which is not equivalent, so it's not symmetric with respect to the polar axis, which means it's probably not symmetric to the pole. But now I can test out the symmetry with the line, and that gives me r is equal to 2 times sine of pi minus theta, and we'll see if we get the same thing. So r is equal to 2, and I'll use the difference formula, sine of pi times cosine of theta minus cosine of pi times sine of theta for the difference formula. And that just gives me 2 times sine of pi, which is 0, times cosine, minus cosine of pi, which is -1, times sine of theta. This is 0, that becomes positive sine, leaving with r is equal to 2 sine of theta, which is equivalent, so we say it is symmetric with respect to WRT, the line theta equals pi over 2. Now let's double check that it's not symmetric to the pole. I could try plugging in -r, but when I divide by -1, I just get r is equal to -2 sine of theta, which isn't necessarily the same. So definitely that test doesn't work, but I can also try r is equal to 2 times sine of theta plus pi, which gives me r is equal to 2 times the sum formula for sine, which is sine theta, cosine of pi, plus cosine of theta times sine of pi, which simplifies to 2 times sine of theta times -1 for cosine of pi, plus cosine of theta times sine of pi, which is 0. So the right term goes to 0, but the left term is negative sine. So r is equal to -2 sine of theta, which again isn't equivalent. So we're only symmetric with respect to the line. Theta is equal to pi over 2. So just as a reminder, these three tests are sufficient, meaning finding that out guarantees that it's symmetric to that axis, but the fact that the symmetry with the pole didn't work out for either of them doesn't necessarily mean that it wouldn't be symmetric to the pole. We would find that out by graphing the function and seeing it. But knowing some of this information ahead of time helps you graph. So in the next lesson, I'll show you how we can use that information to help us graph the function by plotting points. And that is how you test polar equations for symmetry.